We are working with the data that you collected yesterday. You've done bar graphs, most of you. You know that the numbers here along the side are numbers of individuals that fall in a particular grouping, and your bars are going to go up like that. Now, the question is, how do you figure out these groups? Who read the lab? How many groups do you want to end up with? 5 to 7. Yeah. If you end up with 5, that's okay. If you end up with 6, that's okay. If you end up with 7, that's okay. Any one of those. In order to do that, your best bet is to go back to your data, look at your range, and now you will actually subtract it. So let's say that I measured pinkies and I had, my smallest measurement was 2.0 centimeters, which would be like the scrubbiest little pinky ever. And then I had somebody with long ET fingers who had an 8.0 centimeter pinky. Some crazy pinkies. My range is 2 to 8. To find out how big I want those little groupings to be, I am going to go ahead and say, okay, well, 8 minus 2 is 6 centimeters. I want, let's say I want 5 groups. I'm going to take that 6 centimeters and divide it by 5. How big are my groups going to be? 6 divided by 5, 1.2 centimeters. So my first group is going to be 2.0. Oh, let me make that a finer tip. Make that really fine. 2.0 to, I'm now going to add the 1.2 to 3.2. Where does my next group start? 3.3. Because I can't have any measurements that will fit in 2 groups. So 3.32, and I'm going to add the 1.2 again. What do I get? 4.5. Okay. My next group starts where, Gavin?
Looks like next box.
Would start with what value? Discuss it with your peers. Where's your next where's your next grouping going to start, Luke? 4.6. And I'm going to add that 1.2 again. So I'm going to go to 5.8, and then I will go, what, 5.9. So, yeah, 7.1, 7.2 takes me up. Now, 7.2 takes me up above my largest measurement, because that would get me, what, 8.4. Sometimes you get that. If you do what I recommend doing, do this in pencil, number 1, because if I do that, I'm going to try to have symmetry on either end of my range. If you went out and gathered more data, is it possible there's somebody out there who has a pinky smaller than 2 centimeters? Yeah, there is. Is it possible there's somebody who has a pinky bigger than 8 centimeters? Yeah, there is. I haven't met him because that's a big pinky, but that's okay. What I would do, if I get to here and I'm a good chunk over my top end, I would go back and I would change this. I would say, okay, well, let's go 1.8 to 3, 3.1 to, what, 4.3. And then I'm going to end up at, what, like 8.2. So I'm going to be a little bit over my top and bottom values, but it's symmetrical. I'm 0.2 centimeters under my bottom value at the bottom end, and I'm 0.2 centimeters above my top value at the top end. Does that make sense? Okay, there are colored pencils over there. As I said, I think this will be the 3rd time, maybe the 4th. I'll say it a few more times. Please, for the love of all that is sacred, graph in pencil first. Graph in pencil. Then you can color it all pretty with markers or highlighters or colored pencils or whatever else you want, but please, for the love of Pete, start it in pencil, because it just avoids a lot of heartache. So I'm going to turn on Pandora. I'm going to float around while you're graphing. Then we're going to start comparing the shapes of your graphs. Okay, go. We are showing the distribution of a trait in a population. Where are the most individuals in this population that was measured in terms of their measurements? Where do they fall? At one of the ends or in the middle? In the middle. Nothing like being average. There are a lot of people who are average. There are a few people who are exceptional at each end. Now, this is probably, I'm going to guess, I'm not counting, probably like 30 people's data or so, maybe 32. I don't know, I think this group went out and got some people in the hallway. When we look at a distribution, we generally do this. We sort of lay a line on top of it. I'll do that in a darker color. Okay, I'll do that in sort of a darker color. What does that distribution look like? What does that line that I laid on top of it look an awful lot like? A hill, a hump, a lump. This is pretty darn close to what is called a normal distribution. Seems to me you've seen that word someplace before, perhaps on your vocabulary sheet. Sometimes this gets called a bell curve because it looks like a bell. The hump is in the middle. What this means, hey, folks, you should be paying attention to this. This is important. So if you're still working, you should pause for a moment. What this means is that the most common value, the measurement that the most people have, also happens to be in the sort of arithmetic mean. It's in the middle. We can equate this to shoe size. I have a young man in another class who I was joking about, oh, you should bring in a pair of shoes. Just go to Goodwill and get a pair of shoes and stick them in your chem drawer so that you've got them. And he said, I wear size 16s. There are no shoes for me at Goodwill. Oh, you're right, sir. There are not. I have the single most common shoe size for females. I wear a size 8. It is dead average. At the point in the year when winter boots are on sale in the spring or sandals are on sale in the fall, there are lots of size 10 and 11 in women's shoes, and there are lots of size 4 and size 5 in women's shoes. Why? There aren't a whole lot of women with size 4 or 5 feet, and there aren't a whole lot of women with size 10 or 11 feet. Do you think there are any size 8s? No. Because it's really, really common. Lots of women have size 8 shoes. It's right in the middle. That's a normal distribution. This, what was this characteristic, Kaylee? What were you guys measuring? This was wrist circumference. Okay, so we can look at this distribution and say the majority of people fall right in the middle of the distribution. This is a normal distribution. Now, is there any kind of advantage, head up Isaiah, is there any kind of advantage to a person in having a larger or smaller wrist? Probably not. Probably not. We're not living in a culture where you have to like arm wrestle to survive. If you did, maybe having like really big, strong wrists would be a bonus, and having little tiny ones that snapped would mean you didn't make it. But we don't live in that culture. Okay, let's look at a few others. Let's try to lay a line over top of this. Let's lay a line over this data. That's some nice data there. Does the line that we could lay over this look the same as the line we laid over the last one? No. Where's the hump? Is it in the middle? It's towards the bottom. It's close, but it's actually a little bit towards the bottom. This distribution is skewed. This is a skewed distribution. And if you take probability and statistics with Mr. Andres, you will learn more about distributions than you ever wanted to know, and you'll talk about right and left skew. We don't do that in here. For one thing, I can't tell left from right. For another thing, they're not as obvious as you would think. So I tend to talk here about skewed towards the bottom, skewed towards the top. This distribution would be skewed towards the bottom a little bit. We have more individuals a little bit towards the bottom who have a common value. Which, what data is this? This is height? Okay. Oh, that's interesting. So even with a few really tall people in the class, we skewed shorter. Interesting. Now, if you went out and measured, now this is probably what, 29 or 30 people? maybe 24. Do you think that if you went out and measured 1,000 people, your distribution would change? Do you think if you segregated males and females onto two different graphs, do you think that would change your distribution? No. Overall, they would probably both be normal distributions. We skewed a little on the low side. Basically, that means we got lots of short folks in here. I am dead average for an American female. American female average height is 5'5". I am 5'5". If you are above 5'5" for an American female, you are above average. If you are below 5'5", you're below average vertically. You may be above average in lots of other ways. For American males, 5'10" is average. If you're above 5'10", you're above average height. If you're below 5'10", you are below average height. Looking at these distributions, hey Gavin, zip. Looking at these distributions helps us understand how a trait is distributed in a population. Let's do one more. Let's do something really weird. We've got at least one that's kind of strange. Oh, here it is. Look at that. Would the line that you could lay over this look the same as the one you laid over the other two? Not at all. It would look something like this. What's that song? My something's camel has two humps. What? Yeah, my whatever. I don't know the song. Anyway, some kind of stupid camp song from 1 billion years ago. So, the most common measurement in a distribution is called the what? Look at your paper. You can cheat. Look at your paper. It's not cheating, really. Most common measurement is called the mode. Thanks, Isaiah. Most common measurement is called the mode. The most common measurement occurs in the tallest part of the graph. Well, this has multiple tall parts. Guess what this distribution is called? Bimodal. Yep. This is a bimodal distribution. Bimodal. It has two modes. You can have more than that, but at the very base, this has two modes. So what that means is you got people on the low part, you got people on the high part. This one's not all that extreme. Here's the thing about distributions and sample size. You measured under 30 people. I think a couple groups got like 31. Is that a big sample size? That's tiny. The larger your sample size in general, the closer to normal distribution you get for just about any trait. Just about any trait, if you get a big enough sample, will start to move towards normal distribution. There are some exceptions. There are things that are distinctly bimodal. There are things that are skewed. But in general, for many, many traits in many species, any trait you can measure starts to look normal with a big enough sample. Okay. So, who here likes sci-fi, adventure, post-apocalyptic fiction kind of stuff? No? 2 of you? Okay. I got to come up with a better example. Action movies? Okay. One of my best friends who has her master's degree in math and is a very smart person, her criteria for watching a movie is, are there explosions? If the answer is no, she will not watch the movie. Okay. So imagine a world, some setting for some kind of action movie, where the world is populated by random sharp-bladed ceiling fans that operate at a height of 5 feet 9 inches above the ground. Who in this room survives? I do. No, you don't. You're gone. So, in that world, is there an advantage to having a lower value? Oh, yeah. Absolutely. Having a higher value means at some point you're probably going to forget and stand up and get your head chopped off. This is a horrible world. I don't want to live in this world. Horrible world. What about a world in which all food, all the calories available for your species, humans, or we can call you whatever we want, is only to be found in little tiny small cubby holes. Who has the advantage?
Small wrist.
Little tiny, okay, people with small wrists, people with small hands. You know, what, yeah. So there are some pretty bizarre scenarios that we can think about for, you know, is there an advantage to having big heads or, you know, large hand spans? You must obtain all food by palming it. I'm going to do really badly at this because I have stubby hands. I will starve because I can't palm a whole lot. Okay, show off. So you have to think about scenarios in which there would be an advantage to having a really large measurement. Stop it. Stop palming things. Show-offs. Or an advantage to having a really tiny measurement. Okay? That's what I want to leave you with. Finishing those questions and finishing your graphs up, if you need to finish coloring and everything, that is homework. These are due tomorrow when you walk in. Tomorrow when you walk in, we're going to take what we've done here and we're going to start talking about evolution and shifts in distribution. Because that's really all evolution is. Amazing. Amazing. So, questions, comments, concerns? 9? Okay. That's it. You've got the questions for homework. You've got any finishing up that you need to do on the graph for homework. Mr. Maple and I are going to circulate and discuss with you.